name equivalency, as I was telling that in this case we have got two different types whose equivalency we want to establish, and then for example, this type def int value and type def int total. So, here we are defining two different types value and total, though they are both of them are of type integer, but they are new types now. So, they are given two new names, value is a name and total is a name. Now, we have got two variables var1 and var2 of type value, and var3 and var4 they are of type total. Now, variables var1 and var2, so they are name equivalent, and similarly var3 and var4 they are also name equivalent, but this variable var1 and var4 they are not name equivalent, because they are the names of different types, because they are the var1 is of type value and var4 is of type total, though ultimately both of them are boiling down to integers, but name equivalency will not check that way. So, it will be just looking into the immediate type, and based on that it will be giving us the type of the variable. So, that is the name equivalency. Now, another case is the structural equivalency. It will check the structure of the type. So, it will determine equivalency by checking whether they have some same constructor applied to structurally equivalent types. So, if we have got say type say integer, if we have got say types say integer, if we have got say type say say one type is say the previous example as I was taking that type def integer value and type def integer number. Now, if I have got two variables x and y, where x is of type value and y is of type number, then for structural equivalency they will go down. So, it will come to these integer levels and then they will be declared as equivalent. So, this check is done recursively, like if it is one step further. So, till you reach a basic type, so the check will continue. So, it will bring it down to the basic level, and that basic level it will check whether they are going to be of same type or not. So, they will be checked recursively. So, if I have got types I1 T1 an array of whose type is whose size is I1 and type of individual elements T1, and we have got another array whose size is I2 and type is T2, they will be said to be structurally equivalent if I1 and I2 they are equal and T1 and T2 they are structurally equivalent. So, this is like if I have got say one integer array. So, this I1 equal to say 50 and I2 equal to say 100, though both T1 and T2 are integers. So, this is also integer, this is also integer. So, in that case, so in that case, so I1 and I2 they are not of same type. So, naturally I will not have this the overall the same size. I1 and I2 are of this not same size. So, if I have got an x which is array 50 int and we have got another array y which is also a variable y which is of type array of 100 integers, then if you try to write say y equal to x, then this will give rise to a type error, because because they are basic values. So, this is 100 and this is 50, though the basic types are integer, but it will give rise to an error. So, we can so this is the structural equivalency, because this I1 and I2 these values are not matching. So, they are not structurally equivalent. So, sometimes we use a directed acyclic graph for representing the types. So, type expression it can be represented as a directed acyclic graph or a tree. So, both of them are possible. So, for example, if we have got a record consisting of the fields length and word, where length is an integer and word is an array of 10 characters, then this record is the overall type. So, this is a cross product of so at the lowest level you have got this left side, this length and integer. So, this is length cross integer. So, that is there, and you have got this word cross array, and that array is again this 10 character. So, this 10 character is here. So, that is a product, and then we have got the cross product of this word and array. So, that gives rise to this part, and then we have to go at this point. So, we have got the cross product of the whole thing. So, that is the record. So, in this way we can have some tree type of representation for this particular declaration. So, there can be directed acyclic graph also, like if at the lowest level it may so happen that this one instead of being a character. So, this may be an integer. If that is an integer, then this link instead of going here, so it can point to this. Okay. So, the second link of the array. So, instead of going there, so it may point to something like that. So, this way I can have a directed acyclic graph. So, that is not a tree now, because this node so the overall structure is like this: record. So, this is length, and this one is array, this is word array, this is 10, and this is integer, and then the other one of this also here. So, this is a directed acyclic graph representation if this character is replaced by integer. So, we can have all these representations of this type, and then we can check for the type equivalency. So, this is a function that checks for this equivalency of this directed acyclic graphs. Like if S and T represents the same basic type, then return type is true. So, this is the first rule. So, if S and T they are of basic type, say both are integer or real or character or boolean like that. So, in that case it will return that S and T are equivalent. If S is an array I 1 T 1 and T is another array I 2 T 2. So, in that case we have to if I 1 and I 2 these two values are same, then you need to check whether this T 1 and T 2 they are of same equivalent type or not. So, accordingly it is calling this function DAG equivalency recursively with the parameters T 1 and T 2. Otherwise, it will return false. So, if I 1 I 2 are not same, in that case it will say that they are not equivalent. Otherwise, it will depend on the types of this T 1 and T 2. Now, if S is some record type of structure S 1 cross S 2 and T is another record T 1 cross T 2, then we have to go for the equivalency check of S 1 and T 1 and further S 2 and T 2. So, the return value will depend on the equivalency of S 1 T 1 and equivalency of S 2 T 2. So, it checks the DAG equivalency of S 1 T 1 and DAG equivalency of S 2 T 2. So, after this equivalency checks, if both of them return true, then only it will return true, otherwise it will return false. Now, if S is a pointer, if S is a pointer S 1 and T is a pointer T 1. So, they are two pointers. So, then it will be returning the DAG equivalency of S 1 and T 1, because if they S 1 and T 1 they are equivalent, then this S is a S and T. So, they are also pointers of similar types. So, as a result they are declared to be equivalent. Now, if S and T they happens to be function call. So, if that is S goes from S 1 to S 2, its domain is S 1 and range is S 2, and T goes from T 1 to T 2, that is to where T 1 is the domain and T 2 is the range. Then it will be checking the DAG equivalency of S 1 T 1 to see that their domains are same, and it will check the DAG equivalency of S 2 T 2 to check that their ranges are same. So, if they are correct, then it is fine. And so, otherwise if S and T do not satisfy, do not come into any of these 5 rules that we have, in that case it is returning false. So, that way it is telling that okay, the S and T are not equivalent. So, this function DAG equivalency, so it can be made a part of the compiler type checking procedure, and then it can check this equivalency rules and see whether two expressions are two expression or two function or any basic object that you have in the language. So, they are of same type or not. So, this DAG equivalency check can be used. So, there may be some cycles at some types of representation. So, this is particularly true when you are having say pointers. So, that is a cyclical representation, like in many languages, like this is an example from C language where we have got a list. Okay. So, in this list, so as the name as the structure suggests, so you can understand that this is actually talking about something like this. So, these individual blocks, they have got a value and a pointer to the next field. So, this field is called next, it is pointing to the next element. So, this is again pointing to the next element. So, that way it is there. Now, how do we represent the type? So, in C language the syntax for that is something like this. So, we define the value and the struct list star next. So, this is struct list star. So, this part constitutes the type of the variable next. Okay. So, next is a variable of type struct list star, that is it is a pointer to structure list. So, this is a pointer to that. So, when you draw the corresponding DAG, directed acyclic graph graph representation. So, it no more remains a DAG. So, it is no more an acyclic representation. So, if you are trying to do it is in an acyclic fashion, then it will be like this. So, this is we have got this list which is a record, and ultimately this pointer is a pointer to list. However, this is not always very suitable, because as if we are trying to check for this type equivalency and all, then at this point there may be difficulty, because this is where is it pointing to. So, you can have a cyclical representation here, that this pointer is a pointer to the list only. So, that way many times it helps in the type checking. So, both the representations are used. So, it is up to the compiler designer to check to see like which option should be used, and depending on that can choose a proper part, so that this operation becomes simple. Okay, this check rules become simple. So, most programming languages including C, they use the acyclic representation. Okay. So, type names are to be declared before using it, excepting the pointers. So, excepting pointers, for everywhere else the type names are to be predefined. Like you cannot have something like this, that you define a variable of type value. So, value variable 1, and sometime later you declare you have the type definition for value. So, type def int value. So, it is coming sometime later. So, that cannot be the case. So, it has to be the other way. So, this one should come first, and then only the variable declarations can come. So, type names are to be declared before using it, excepting the pointer. So, pointers you can do. So, it may so happen that this is you can say that this is a value star var1. So, var1 is a variable of type pointer to type value. Okay. So, since this is a pointer ultimately, so pointer is a memory address. So, it is possible to allocate space for var1 and all. So, this is allowed in the language. So, but the compiler designer does not know what is the type of var1, actual type of var1. So, if it is looking for name equivalency, it is fine, but if it is looking for say structural equivalency of var1 with something else, so it will not be able to do that, because it does not know the definition of value at this point of time. So, that way it can be problematic. However, so they are accepting pointers. So, everywhere else, so they are to be declared before using it, and name of the structure is also part of the type. So, name of the structure like this value, so that is a part of the type. Equivalency test stops when a structure is reached. So, that way it will be so this so whenever you are checking for this equivalency of say var1 and some var2, then while doing that if you draw the corresponding DAGs. So, whenever at the leaf level you have got this structure, so it cannot be beyond that. So, it will stop at that point. So, at this point they are equivalent if they point to the same structure name and non-equivalent otherwise. So, if this is pointing to say list and say this is pointing to say list 1 and this is pointing to list 2. So, in that case they are taken to be structurally non-equivalent, though it may so happen that list 1 and list 2, if you refine it further. So, they are boiling down to same set of fields in them. So, but this we have to stop at some point of time. So, this type check, so it stops at that point. So, it does not go beyond the point where it has seen some structure. Okay. So, it will stop at that point. Sometimes we need to do type conversion, like from one type we need to convert to another type. So, it refers to the local modification of type of a variable or sub expression. So, this is commonly known as this type coercion sort of thing. So, it may be necessary to add an integer quantity to a real variable. However, the language may require both the operands to be of same type. As I was telling previously, that I may require that x plus y. So, z equal to x plus y has to be done, and this x is of type integer and this y is of type real. So, whenever this language says that whenever you have got this plus operator, so they are the operands should be of same type, x and y they should be of same type, but it may not happen because at some points of time so it may be that they are of different types, and this may not be taken as an error. So, whenever though the language says that they should be of same type, x sub expression should be of same type, but it may be that it will not be completely an error. So, it can give a warning, the compiler designer can produce an warning that these operands are of two different types for this particular operator. However, the major difficulty that we have is that this integer and real, their sizes are not same. Very often this integer may be of 4 bytes and this real may be of 6 bytes. So, now whenever you are doing this addition, so we need to convert this 4 bytes to 6 bytes, then only you can really do this addition, otherwise it will be a problem. So, modifying an integer variable to real, it will require more space. So, to treat integer operand as as a real operand locally and perform the operation. So, one option is that in the whenever you find like this, so you have defined like integer x, real y in your program. So, what the compiler may do is that it will convert this type of this integer to real. So, type of this x to real. So, that way it will always take x as a real variable, but if you do that, then the difficulty is that for the entire program, so this x variables representation will be 6 bytes. So, wherever this x will be referred to, it will require 6 bytes. So, that way the space required by the program will be large. So, what the suggestion is that since at this point only we have got this addition with real. So, for this particular statement only we modify the type of x. So, this is the local changing of this type, and this may be done explicitly or implicitly either. So, if it is done implicitly, then it is called this is known as type coercion. So, this is an explicit definition. So, this is so this y equal to x by y. So, since this x is a integer variable, so we convert it locally to a float by doing a type casting. Okay. And then this is the type coercion. So, this is basically this. So, this x you can also write like x by 14.0. So, in that case implicitly it will convert this x to float and then assign it to y, whereas this one. So, this is explicit, and here the programmer has explicitly mentioned that this has to be done in this fashion. So, compilers can perform this static type checking, and dynamic type checking is definitely costly. So, types are normally represented as type expressions, and type checking can be performed by syntax directed techniques, and type graphs may be compared to check for type equivalency. So, next we will be doing a few exercises on this type expression. So, the first one that we will look into is for the type coercion. So, we have previously seen that type coercion this type check of this expression, like say E producing E 1 plus E 2. So, previously we said that if this a type of E 1 and type of E 2 are same, then it is fine, otherwise there is a problem. So, we can modify that check and we can do it like this. So, first we can check E 1 dot type and E 2 dot type. Check E 1 dot type and E 2 dot type to be one of the basic types like character, integer, then float, double. So, if we are talking in terms of C language, so these are the basic types that we have. So, it has to be one of those types. So, if it happens to be like that, then if other types, if it is not one of those basic types, then we can say that E dot type is type error. So, this is a type error. Otherwise, for if E 1 dot type is, so if E 1 dot type is float and E 2 dot type is also float, if both of them are float, then we can say that this E dot type is equal to float. Similarly, if both of them are double, else if E 1 dot type equal to double and E 2 dot type equal to double, then we can say that E dot type equal to double, else if E 1 dot type equal to integer and E 2 dot type is also equal to integer. So, in that case E dot type is equal to integer, else E dot type equal to character. So, this may be the detailed set of rules to see that it falls into one of these operator types and it is doing the operation properly. Okay. So, we can do this check, and for other rules also we can do this thing. Next we will be looking into another example of say one list type. So, this is again a C declaration, structure list 1, that has got fields like character x, integer y, integer a 100. And there is another structure list 2, and there we have got character a b c, then integer x y, then integer array 100. Now, whether they are type equivalent or not, if we want to check, then we will be able to construct the corresponding DAGs. So, this is a record, it has got 3 parts in it. This one is having x character, this is y integer and this is having a array, and then we have got 100 and integer. Now, this one, so list 2 is a record it also has got 3 fields in it. So, one is ABC character, then this XY character integer, and this is an array AR hundred integer. So, after constructing these two such DAGs, we can see that they are going to be equivalent, because at the lowest level you have got this character integer array 100 integer. So, here also you have got character integer array 100 integer. So, they are type equivalent. So, these are type equivalent. So, if you take some other example, so it may be that they are not type equivalent. So, let us take another example where this first list is again a structure list 1, and there we have got integer value and this structure list 1 star next, and we have got the structure list 2 integer value and structure list 2 star next. So, here also if we draw the corresponding trees, so DAGs, so this is list 1 equal to record, and then we have got this two parts in it. One is integer value, and here I have got this next, which is a pointer to list 1, and here this list 2 is equal to record, then this is two part in it, one is value integer and the other part is next, it is a pointer, but pointer to list 2. Okay. Now, these are non equivalent, because when it comes to this point, so this up to this much it is fine, so this much, but this is a pointer to list 1 and this is a pointer to list 2. As a result, so these two are going to be non equivalent. Even if we, so this is an acyclic representation. So, even if we have got a cyclic representation where instead of doing it like this, so we give it back to this point, then also it does not help, because here also it is telling that it is a pointer to list 2. So, that as the equivalency check we have said that it stops when it reaches the basic structure. Okay. So, it will stop at this point, and here it will find that this is a list 2, this is list 1, their records are different. So, they are non equivalent. So, whatever way we represent it, so these two types are non equivalent types. Okay. Thank you.